Welcome to the Grade 12 Physical Sciences work past paper by November 2022. So I'll be drawing it, what is this? Just hold on. So I'll be drawing this question out over so that we can have a nice idea of what is going on exactly. So it says here we have a 12 kilogram block, and oops, there's a triangle, 12 kg block that's initially at rest at point A, that is over here, point A, so the velocity is 0. At the bottom of a rough surface, so we have a friction. And in an inclined plane, the block is pulled up the inclined plane by a constant force. So I'm going to redraw this, but remember it starts by A, okay? 12 kg is being pulled up by a constant force, some applied force. It reaches B, which is vertical, okay, so it says just 4.5 meters above the ground. With a speed of, it reaches B at a speed of 2.25 meters per second. So we're just going to be looking at this part for now. So 5.1 is a definition. 5.2, draw a labeled free body diagram for the block when it is pulled up the inclined plane. So we're going to take a look at our block. This is a Newton 2 type of, or related to it. So we have a weight because it has a mass, and we have to the normal that way, because it's 9 degrees to surface. We have an applied force this way and a friction in the same plane, kinetic friction. Now you can break up all your components, but yeah, I mean you can if you want, but that's acceptable if you want your quick 4 marks. It'll take you like what, 20 seconds to draw that. So 4 marks, 4 vectors, makes sense. Next one, 5.3. Calculate the, I'm just gonna take this out the way for now and bring this down. This diagram is very important. Actually, I shouldn't do that. Just leave it there. 5.3. Calculate the total work done on the block by the non-conservative forces when the block is moved from A to B. So they want you to work this out. So let's take a look at what our formulas are. So I have here these two specifically that has to do with the total work done by the non-conservative forces as the block is moved from A to B. So the block is being moved from, as we see here, A to B. So if we go with the second formula, we're trying to work out the work of, first we have to decide what the non-conservative forces are, right? So if you look at our free body diagram, we have a weight. Now we know that's conservative. We have a normal conservative, but the friction is non-conservative and the applied force is also non-conservative. So we have two non-conservative forces. We don't know what their values are, but so if we were to now work out, for instance, work of friction plus the work of the applied force, we're gonna have like three unknowns. We're gonna have that, and then inside there we're gonna have the friction value and the applied force value at that angle. So it's not going to be very, it's not going to work. Yeah, not going to work, eh? So let's work something else out. That would be that one. So what about this? So we find the non-conservative work. Just write this thing properly. Let's put this formula down. Let's break it up quick. So we have a half mv squared plus mgh. Well, what am I doing? That's with the final minus half. Let me just fill this out quick. Before I fill it out, so we need masses, initial velocities and final velocities for EK, delta EK, right? And for EP we need mg and h's. So we know, we want to know this. We know the mass of the object. We know initial velocity, final velocity. We know the mass of the object. We know the gravitational acceleration. And we know the heights, or the one height and the other height. So we actually know everything here to work out our work done by the non-conservative forces. So let me fill it out quick. So this will work. It will work well. All right, so hold on. All right, so I broke it up, and we know mass, final velocity. We know the mass. We know initial velocity. We know the mass, gravitational height, mass, height. We know all these things. So this is gonna be a straight up, easy 4 marks for us. Now, So the mass is, what was it in 12? Yeah, 12 kgs. So I'm going to fill out all the masses. For the end of initial velocity was 0, and we ended up going 2.25, right? So initial velocity is 0, and final velocity is 2.25 for this specific case. Our initial height will be 0, and our final height, we go up to a height of 4.5 meters. So I'll fill it in quick. Right, so for this piece here, I subbed in, but for this piece, I just made it a 0 because I know the initial velocity is a 0, so that whole term will be zeroed out. If you look at my third term, MGH, HF, which is the final height, we have 12, 10, now I can tell, will work out. But this initial height here is a 0, so that term also zeroes out. So I'm left with this, type in my calculator, and I end up with the answer of 559.85 joules. Easy peasy, 4 marks. Alright, but the next question is the one that is quite tough. So let's take a look. 5.4 tells us the same constant force, so whatever the force was initially, it's going to be the same force again, now moves a block at a constant velocity across the rough horizontal surface from points B to C. Let's say it's C over here. So we have the same force value, the same applied force. So make sure we understand that it's the same. Just put a little highlight in there. It's good to do this in the test, eh? At a constant velocity, so it means that my velocity will also be 2.25. It doesn't change. And F is parallel. If you look at the picture, nothing different. And if we look below the picture, the magnitude of the constant frictional force acting on a block while it's moving from point B to C is 42 newtons larger. There's the friction on the left here. This friction is 42 newtons larger. So there's two ways we can do this, but I'll do the one way. So we have, let's just say it's force 1 and a friction 1, friction 2. So friction 2 is equal to friction 1 plus 42 newtons. That's important. It's like a simultaneous. This question is like a simultaneous equation in a simultaneous equation, cancelling certain things out, subbing out like twice. It can be quite an involved thing. So let's see if we can sort of figure this out. So there we go. Now that is the information they gave us. So we have to now find the distance from B to C, or basically the displacement BC. How are we going to find this thing? So in this type of thing, I would leave this question for last. It is very involved. You have to have quite a lot of insight, and you have to bring all this knowledge you have together. So I'm going to list a few more equations here on the right that we can see why it can be quite involved. So we have to bring in prior knowledge from grade 11, which is Newton 2, F net equals ma. We can use two-dimensional motion in a straight line, using our Vadix thing or summary we got there, and then incorporate that within our work system of formulae and ideas with our potential energy, kinetic energy, mechanical energy, and bring all those things in. You have conservative and non-conservative forces impacting the work. It's quite involved. So I would actually just leave this question and say, that's complicated. I'm leave it for last, because I'd say that this is definitely a level 4 question. So let's take a look. Alright, so I basically summarized everything we know. It'll take quite a while, but if you look at our forces, that's like the thing they say, like all these forces like equating, or sort of, it's like the applied force at the top will be equal to the frictional force at the top. But F2, so we're looking here now, so the applied force at the top is equal to the frictional force there, F2, and frictional force 2 is 42 newtons higher than the first frictional force by the incline, so these two. F2 is 42 newtons larger, and also then I just drew it both ways if we need to maybe sub it in like that. So we have an initial velocity of 2.25, final velocity of 2.25, meaning there's no acceleration. The time's not mentioned, so we can't use it. And delta x equals 0. We don't know what it is. Oh, that's what we want, sorry. We want to know what delta x is. So we have to incorporate delta x in our formula somewhere. and mass is 12, gravitation these we don't care about. So let's take a look. I'll also do the new free body diagram for when it's on a horizontal surface. If the block's on that horizontal surface, this is what it'll look like. So we're just going to ignore those two. We're moving in the x direction. Right. So knowing this, I'll probably want to write it a different way, but Fa is equal to F2, friction 2 equals F1 plus 42. So like these three, let's call them terms, are all related to, or all identical to each other. Make a rectangle. So let's work with the incline. Now, the previous thing we worked out was the work non-conserved, and we got a value of 559,58. So there are about a few ways to do this, but let's go with one of the formulae with this one, and then I'll do one like that. So work non-conserved equals work non-conserved 1 plus work non-conserved 2. So on this inclined plane, I drew, rub this thing out, but we have an applied force. So we have work plus work friction. And then we have to break that up using our initial work equation over here. There it is, I broke it up, and we worked out work non-conserved earlier as 559,58. Let's just give it a WNZ for now. And that's sub in what we can. There we go, subbed it in. So I said cos of 0 for the force applied, looking at this situation. So in the delta x, the direction of motion is this way, correct? It's going in that direction. So the applied force is in the same direction, so there's a 0 degree deviation, and the friction is in the opposite direction, so it'll be a cos of 180. Whoops, made a mistake here. This W shouldn't be here. We broke it up. Making mistakes like this in a video. Yeah. Okay, so there we go. All better. So now we will just get that cos out the way. So it's Fa delta x. And that's just that cos 1 just falls away. Minus the F1 delta x, which is equal to 559,58. But see, now we worked this out, or we identified this type of thing earlier, and now we have this Fa delta x minus the F1 delta x. But Fa is F1 plus 42. So if we maybe substitute that in there, will we be able to solve it? Let's take a look. So we end up with this. Now, this is a situation where, remember when you were in grade 9, you're like, why are we doing all this factorization? Why am I doing factorization? It's like so ridiculous. Look at it now it's actually quite useful. Look at those funny shapes. Now, we'll have to factorize out that delta x, and we end up with F1 plus 42 minus F1. And that just cancels itself out. We get 42 delta x equals 559,98 divided through by 42, and we get what? 13,32 meters. Yeah, that was a bloody adventure. Now, yeah, well, this is the level 4 question for work, one of them. And it's tough, eh? It's like a simultaneous equation where you have to like eliminate variables using simultaneous equations, having to know that, putting things in relationships, knowing which equation to use. Oh, wow, quite a toughie. So, but let me do the other version where we, instead of saying WFA plus WV friction 1, let's go with this equation and see if we can fill that out. Hold on. Alright, so we can do this. The interesting thing is we actually worked this out earlier, so we actually have a value for this. We don't need to redo the whole damn thing. But but we can break this up. This is the method I like. So this will be Fnet delta x cos cos of theta. And our Fnet will be, or when I say Fnet, will be the Fnet conservative forces. Just careful that. So that will be our force applied and minus our friction. Not F2, F1, we're going up the plane. So, and delta x and cos of theta. Now, going up the plane, it said that it's moving up the plane, so FA will be a positive and our friction will be a negative going up the plane. And they will all be in the same, the Fnet will be in the same direction as the delta x. So we just put this, I'm just leave this delta ek here for now. This thing, I'll do it again. And yeah, we just sub in the values in. So we have FA minus friction 1 delta x cos of 0, because it's in the same direction as the displacement, the Fnet now, in terms of the conservative forces. And we actually worked this out, and that will be equal to 559.58. I'm just keeping the previous answer over here so we can take a look at it. And there we go. So now this is now the important part that we have to sub in here to try and eliminate something. So we just left with our delta x we can play with. Oh, cos of 0 to 0. So I'm going to do it now. So I'm going to replace that FA, which is over here, and I'm going to replace it with that F1 plus 42. F1 plus 42, emphasize brackets, minus F1 delta x, that cos 0 just becomes a 1, and we have 559.58. This is actually I prefer this method to the previous one, but if you look at the memo, it's probably like 8 methods or something. So this, look on left term here, we are F1s will just subtract out. We left with 42 delta x equals 559.58, and we will end up with this, just like the previous one, with 13.32 meters. Look here, really involved question. Yeah, my advice is leave work for last. It's quite fun once you get to know it. You just need a lot of practice, but time-wise, you're all writing tomorrow, so let's maybe leave this for last. All right. Don't forget to like and subscribe, and all that. All right, bye.